Hey there guys, Mr. Carlson here. In this video what we're going to cover is two things. One thing is partial pressure and the other thing is mole fraction. Last week you guys looked at some problems with partial pressure. Maybe you remember them, maybe you don't, so that might be a little bit of a review for you. But the new thing is working with this thing called mole fraction. So let's just review real quick. When we're talking about partial pressures, what are we talking about? So let's say I have a container here that has three different gases. So we've got these blue molecules, green ones, and red molecules in this container that has a volume of 5 liters. And let's say that the temperature of this container is 273 degrees Kelvin. For partial pressure, what we're really essentially looking at is that, so the total pressure of this whole thing is going to be equal to whatever the pressure of gas 1 is, plus whatever the pressure of gas 2, and then plus whatever the pressure of gas 3 is. So then we can set this up. Remember, using our ideal gas law here, that if we rearrange it, pressure is equal to the number of moles times the gas constant times the temperature divided by volume. And so I just down here, we replace the pressure of gas 1 with nRT over V, and then the pressure of gas 2, the number of moles of gas 2 times R times T divided by V, and same thing for gas 3 would give us the total pressure. And then we could rearrange this further and simplify it even more into just the total number of moles. So adding up the total number of moles for each gas times our gas constant times our temperature divided by our volume. So there's a few different ways that we can think about partial pressures, but the main thing is this, that the total pressure of this is equal to the individual pressures of each gas added together. So now let's just quickly look at an example of using that. So let's say we have a mixture of, let's say we take 46 liters of helium, that's at 25 degrees Celsius and 1 atmosphere. And then we take 12 liters of oxygen or O2 gas, that's at 25 degrees C and 1 atmosphere. And we pump those two gases into a tank that is 5 liters big. What is the partial pressure of each gas and the total pressure of the tank if it's still at 25 degrees Celsius? So we're taking two different volumes of gases, and we're pumping them into a 5-liter tank. And we want to know what is the partial pressure of each of those gases once we pump it into this tank, and what's the total pressure of the tank. So let's think about it like this. We know that the partial pressure, so if we're just, let's think about total pressure first actually. So if I want to figure out the total pressure of the tank, the 5-liter tank, that means I have to add up each individual pressure of those gases. So the first thing I have to do is figure out what is the pressure of helium and what is the pressure of oxygen inside that 5-liter tank. Well, the pressure, if I come over here, the pressure of helium, let's say, is going to be equal to, so coming back up here just so we get a reference here, is going to be equal to the number of particles, or sorry, the number of moles, I should say, times R times T, temperature divided by the volume. If I come back down here, though, I don't know how many moles I have. I have how many liters, I have a volume, I have a temperature, and I have a pressure. So I actually can't solve for the pressure of each gas because I need to know N. I need to know N. The problem doesn't give me N, and so I can't just jump in right away and solve, okay, what's the pressure of helium and what's the pressure of oxygen, and then add them together. I first have to figure out, well, how many moles of each do I have? And so this kind of goes back to the stoichiometry problems that we've been doing. And the way we solve for the number of moles of helium, is going to be, so just again rearranging this equation to solve for N essentially, is going to be pressure times volume divided by R times the temperature. that's going to give me the number of moles. So I have to do that first for each one. So number of moles of O2 will be the same thing, pressure times the volume divided by R times T. So let's plug in our values here. So for helium, and again, what we're going to be using though is before these two gases go in this 5-liter tank. So the pressure before it goes into this tank was 1 atmosphere for helium. So 1 atmosphere times the volume before it goes in here, because we're trying to figure out how many moles, so I have to use the volume before it goes into this 5-liter tank, which was 46 liters of it. So 46 liters divided by our gas constant, 0.08206, and then the temperature, again, before it went into that 5-liter tank, so 25 degrees. Well, it stays 25 degrees, so it's the same temperature the whole time, but converting that into Kelvin would be 298. And we'll just hurry up before we even crunch any numbers here. We'll do the same thing for O2. So this was also at 1 atmosphere of pressure before it goes into the tank. It was 12 liters, 0.08206, and the temperature is the same as the one above. Crunch the numbers, what do we get? 1.9 moles for helium, and for oxygen 0.49 moles. So now I know N, and so now I can solve for what is the, I'll do this over here, I've got N, so now I can figure out what is the pressure of each gas. Pressure of each gas. Using this, the pressure of helium is going to be equal to the number of moles of helium times R times T divided by the volume. And now for this one, now I'm using this 5 liters for the volume, because now I'm figuring out what's the pressure once I take this amount and I put it into this 5-liter tank at 25 degrees Celsius, what's the pressure? And same thing for the pressure of O2 is going to be the same process. Number of moles of O2 times R times T divided by V. So what do we got here? We said 1.9 for helium, so 1.9 times 0.08206 times the temperature, still 25 degrees C, so 298 Kelvin, divided by now 5 liters for the volume. And same thing down here, except for my number of moles is 0.49, so 0.49. Everything else would be the same though. Temperature and volume are still 5 liters and 298 K. Crunch the numbers, and we get a pressure of 9.3 atmospheres for helium, and we get a pressure of 2.4 atmospheres for O2. So that's my partial pressures in this 5-liter tank. The pressure of helium is 9.3 atmospheres in this tank, and the pressure of O2 is 2.4 atmospheres in this tank. The total pressure of the entire thing, the entire mixture, so pressure total, is just these two added together, right? So 9.3 plus 2.4 would give us a total pressure of that tank to be 11.7 atmospheres. And that'd be our final answer there. So there's my partial pressures and then the total pressure. So again, that was kind of a little bit of a review. You guys had already looked at problems like that previously, but I just wanted to do a little bit of a review. Now, the next thing is working with this thing called mole fraction. Mole fraction. Mole fraction is essentially saying this: the number of moles of one component divided by the total number of moles in the whole thing. So it's basically just a ratio. Okay, so it's the ratio of the number of moles of a component gas over the total moles. So if we come back up here, Like if we were to think about the mole fraction of just the blue particles here, it would be the ratio of how many moles of the blue particles do I have divided by the total moles of this whole thing. That's what the mole fraction is. So moles of the component. So I could just as well do like N2 over the total for the mole fraction of a second type of gas in that mixture, right? So this is the symbol we use for mole fraction, okay? And it's also related to the pressure. It's directly proportional to the pressure. So I could just as well say the pressure of gas 1 over the total pressure of the whole thing. That is also the mole fraction. We could use both of these to determine what the mole fraction is because they're directly proportional to each other. So coming down here to look at this example, let's say the partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743 torr. Calculate the mole fraction of O2 present. What they mean by in air, like just in the air, this atmospheric air that's all around us right now, right? So the air that's in the room around you that you're breathing in, which is made up of more than just oxygen, right? There's things like nitrogen and CO2 gas, things like that. And so it's saying that the partial pressure of just the oxygen in the air around you is 156 torr. And the total pressure, or the atmospheric pressure, the total pressure of the whole, everything together is 743 torr. We want to know what the mole fraction is. Well, up here we just said that mole fraction is equal to, and actually I should say, we're looking at the mole fraction of O2 is equal to, we're going to say the pressure of O2 over the total pressure, because that's what this problem is giving us. They're giving us these pressures. So this one's pretty simple, just plugging these in where they go. So the pressure of O2, they told us, is 156 torr. Total pressure, total atmospheric pressure is 743 torr. So let's plug the numbers in here. So 156 divided by 743 is 0.21, we'll say. 0.21. Now, this is a unitless number because it's just a ratio. So let's make a note here that there are no units for mole fraction, because again, it's just a ratio between these two different pressures. So no units for mole fraction. Okay, let's try a second example. Let's say that the mole fraction of nitrogen in, again, air, just in the air around us, is 0.7808. Calculate the partial pressure of N2 in air when the atmospheric pressure is 760 torr. So let's just write out our general equation here. So partial pressure of, and we're just going to put N2, or sorry, not the partial pressure, the mole fraction of N2 is equal to the pressure of N2 over the total pressure of the atmosphere. We can rearrange this equation to solve for different parts, right? So if I wanted to solve for just the pressure of N2, all I have to do is multiply by the total pressure on this side and multiply by the total pressure over here. And so now I've solved for the pressure of N2 is equal to the total pressure of the atmosphere times the mole fraction of N2. And I already know what the mole fraction is. They tell me what it is, 0.7808. And I know the total pressure, 760 torr. So this would just be equal to 760 torr times the mole fraction of N2, which is 0.7808. So the partial pressure of N2 would be, let me punch this into my calculator, 760 times 0.7808 would be 593.4 torr. Notice I didn't have to convert this into atmospheres, by the way, because I'm not using the ideal gas law in this case. I'm just using this equation for mole fraction. So if I had to plug that pressure into our ideal gas law at all, where I'm using the ideal gas law like constant, then I would have to change this into atmospheres. But in this case, I can just keep it as torr for this.